Awesome. Welcome, everyone. This is another fun session with Deep Learning Adventures, a fun, engaging meetup with friends around the country and around the world, where we talk about data science, deep learning, and fun applications of AI. Today, I'm joined by my great friends and co-hosts, Robert and David, as well as friends from all around the country. Welcome, everyone. If you're joining us from YouTube, well, a warm welcome, or other social media, or Kaggle. I'm posting here on our chat. You can find us on Slack as well as on YouTube. And let me share my screen so I can better point at things. So on Meetup, you can find us again on Deep Learning Adventures. We've been tackling these Kaggle mini courses, what it's called, for the recent 3 months. We started with machine learning, some simple data science, and geospatial analysis. We went to computer vision, deep learning. We deployed a model on our phones actually to do flower classifications. We looked at reinforcement learning very briefly using some simulation games, and Robert and Kathleen last time covered their second version of the Pedals to the Metal, where they took a deeper dive into a fun data set related to the capital bike share. Today, we're going to talk a little bit about AI ethics. This is a brand new course from Kaggle. Super excited to cover it with our community. As you can see from my tabs open here, these are all resources that are immediately referenced in this notebook. So a lot of content. Obviously, I didn't have the time to go through all of them, but just looking at the depth and breadth of the research being currently done on this topic, it's something interesting. I'll cover the introduction, then Robert will take over next couple of sections, and then I'll wrap up in the end with the last two. Again, all our sessions are recorded, including this session. If you didn't get the chance to watch it, you can watch it later. Cool. So let me zoom in a little bit so we can do a little bit later. So this course starts really talking about AI and the fact that artificial intelligence is used in so many fields now, within applications, not only in computer vision or text analytics, but also like things like agriculture or surveillance, like video surveillance and so forth, social media, making decisions when a credit card transaction should be approved or not, when a loan should be approved or not, and things like that. So obviously it's used in a lot of fields. And one key thing to keep in mind that with any other technological solution or technical tool, we need to make sure that we are serving humanity and we are serving the people versus unintentionally or intentionally trying to do harm. So that's really this ethical lens that this course is bringing. The bigger picture is there's usually not a clear answer of how to make a model or a process ethical or human-oriented or human-centered. It's a discussion that a group, a company, or organization should take collectively and really visit every step of the process to ensure that there's no unintended harm or bias, as we're going to see soon, or that fairness is basically applied throughout the process. So this course will talk a little bit about human-centered design and what that means, and how can we use AI to better serve the needs of the people that is intended for. We're going to talk a little bit about bias and how can we tell if there's bias in our data set, if there's bias in our model, if there's bias in the way that our model is deployed in production and so forth. We're going to look a little bit about at some fairness metrics. There's a few interesting fairness metrics that we're going to look at some concrete data sets and how that applies, as well as this new concept, what is called a model card, and more companies are currently applying it, of how do you summarize a model? What does it do? What does it not do? How do you share it with a broad audience that is not necessarily super technical? So these are some really interesting topics that we're going to take a deeper dive. And again, the higher level discussion is that this is an ongoing process. You need to really think about this end to end versus just focusing on the data part, the model part, or the people that you're serving part. So it's really a collection of processes. Cool. With that said, I'm gonna stop sharing and hand it over to Robert. And enable screen sharing. Welcome, new friends who just joined us.
Hi, can you see my screen?
Yes.
Excellent. So thank you, George, for that introduction. A couple things to add to that, although I think the most important aspect that was consistent throughout this course was the observation that in the case of ethics in AI, bias in AI, fairness in AI, in many cases, the answer is not cut and dried. In many cases, there's no clear right or wrong answer. It always involves a conversation, a discussion of the trade-offs of different potential impacts and what strategy would produce the best product or best model for the purposes for which it is designed. In that same spirit, I would absolutely encourage this relatively small group of participants who are joining us this evening to please weigh in anytime we reach a topic of interest to you. I think that George and I will be steering the conversation, but I want to make sure that everyone is able to express their points of view. I'm sure that you have had different experiences than we have, and as we said, it's a conversation. So I hope that we have those conversations this evening, at least at a very short version of them anyway. We can fit in this one meetup. So with that said, thank you for joining us tonight. And we'll get started on the second module here with human-centered design for AI. So in this section, we get to see really an overview of human-centered design, which is a field unto itself, and its application to the world of artificial intelligence. And it did kind of strike me as I was going down through each of these 6 aspects that they cover in the approach, how every one of these things really is applicable to product development, to solving problems in general, and has very little specific to AI. There are examples here that are asked about AI that do have certainly some relevance to AI specifically, but in many cases the analytical framework is very general. So the first step that we discuss here is that one should, or that a team should, understand people's needs to define the problem. People could be your customers, could be stakeholders in your problem somehow, or the population in general. It all depends on what problem you're solving. But in order to come up with a good solution to the problem, you always want to consider people. And in many cases, the thing that you really want to ward off here is making sure that you're not producing a solution in search of a problem. If you don't have a problem, then you probably don't need a product. The example shown here is on a company that wants to address the problem of dosage errors for immunosuppressant drugs given to patients after liver transplants. And the idea here is that you should start, before you think about building models or anything, start by observing the way things are currently done. Speak to people who are currently involved in the task, find out what their challenges are. The second point made in the course, before I continue, I should mention that while I'm screen sharing, I have difficulty seeing the chat. So if there's anything in the chat that needs to be addressed, please let me know, one of the other leaders. Thank you.
Yep, we got it.
So the second thing is ask if AI adds any value to your potential solution. So a couple of questions you should ask yourself. Would people generally agree that what you are trying to achieve is a good outcome? This is a question that, okay, they do recommend that teams do ask themselves. It's evident that AI these days is used for a variety of purposes that are certainly a good outcome for someone, although maybe not everyone. In fact, maybe it's a good outcome only for the people running the AI. So this is something to think about. The second point, would non-AI systems, such as rule-based solutions, which are easier to create, audit, and maintain, be less effective than an AI system? And don't reinvent the wheel. If the current versions work just fine, you don't need to go beyond with an AI solution. The third one really gets to the prototypical use case for AI. Is it a task that people can do but they would find boring, repetitive, or otherwise difficult to concentrate on, such as labeling millions of images?
Nobody wants to do that.
But people have to do that before computers can. And the fourth one, have AI solutions proven to be better than other solutions for similar use cases in the past? If you answered no to any of these questions, an AI solution may not be necessary or appropriate. And the example given here is a very apropos one, a disaster response agency working with first responders. Disaster responders may be able to leverage AI products to predict where they might need to rescue people during floods. So this can be an absolutely life-saving endeavor. Time and labor-intensive human review of photos can take time that the rescuers may not have if it is a time-critical situation. So that's a really good use case. I would say that maybe the framing of if you answered no to any of these questions, a solution may not be necessary or appropriate. I think most systems in use today probably answer no to at least one of those questions for one reason or another. But it's definitely useful food for thought in analyzing your systems. Number 3, consider the potential harms that the AI system could cause. Weigh the benefits of using AI against the harms. So the first sentence says it all in that sense, right? The AI system could cause potential harms, but it also could cause benefits that make those harms worth the risk. But you do have to consider your entire design pipeline, all the way from the collection and labeling of data, model training, deployment, a lot of different places where undesirable behavior can enter the chain, and we'll see that later, especially in the bias unit. So you may have, for instance, privacy issues, and there are a number of solutions for dealing with a number of approaches for dealing with privacy problems. Differential privacy, federated learning are two of them that aim to protect privacy of users that may be contributing sensitive information to model development without necessarily explicitly sharing that information in a way that is readable by other users of the same system. So federated learning, it offers a way to train across many users without them having to share their data in that way. Differential privacy is also a good, it's good to test whether systems are sensitive to an individual's presence in the data set or not. If they are sensitive to that, then you may have a problem with privacy. And the example they give here is an online education company that may want to use AI to score essays, but there are some potential issues noted here, such as the potential for the AI system to discriminate against certain types of language.
That was an interesting example to me, right? I mean, we don't think about it, but maybe different groups, or maybe people like me, who come from other countries, maybe we have a different way of expressing ourselves, so maybe the AI system can tune itself on different patterns or maybe different phrasal verbs.
Right, and that may make it perform better or worse on certain groups of people,
Yeah.
which could have adverse effects if the designers are not careful. Prototype, starting with non-AI solutions. This is really not so much an AI specific recommendation, just more of a product development recommendation in general. You always want to keep your potential user base, potential customers in the loop so that you just general business sense, develop prototypes to get some feedback on how people may engage with your system before investing lots and lots of effort in model training that may not turn out to have been useful. They point out that the people giving feedback should have diverse backgrounds. You really want them to be representative of your user base. So if you foresee your product wanting to be, if you foresee the user base of your product being diverse in race, gender, expertise, and other characteristics, then you want to make sure that the people that are going to be serving as your beta testers and feedback for the user interface, that they also embody enough diversity to capture that representation. An example provided is a movie recommendation to users. If just a small number of users are giving their preferences, then maybe you're not getting the overall population's interests. Number 5, provide ways for people to challenge the system. This is really crucial, actually, because no matter how much thought you're going to put into your system, there's always going to be something that you didn't think of. There's going to be ways that your system can be broken, ways that your system can discriminate in ways that you didn't anticipate, ways that it could cause harm in other ways. And you really need to think about all the possible ways in which your system could fail or produce undesirable results, and enable feedback mechanisms that allow people to communicate to your developers that these are problems, so that you can start to think about how you can fix these problems. So the example provided is an online video conferencing company uses AI to automatically blur the background during video calls, but the automatic blurring function may not properly focus on a person's face, and maybe the reason that it's not focusing on a person's face is asymmetric based on the skin tone of that person's face, so it may blur some people's some ethnicities backgrounds more often than others, and this could cause operational and other concerns down the road. So you want to make it possible always for users of the system to be able to reach out to you, to get back to you with relevant input based on their experiences. And 6, building safety measures. Safety measures protect users against harm. So we've talked a little bit about some of these things, but a human red team to play the role of a person trying to manipulate your system into unintended behavior. Try to think of all the ways in which someone could inadvertently misuse your system or intentionally attack your system to produce undesirable results, and then figure out what countermeasures you can take against such manipulations or occurrences. Determine how people in your organization can best monitor the safety of the system once it is live. That goes back to what we were saying in step 5 about just always having mechanisms for people to provide feedback and ways to observe user experiences. Third bullet, explore ways for your system to quickly alert a human when it is faced with a challenging case. That is, related to think of the self-driving car example. You may not want to have self-driving cars 100%. You may want to have a system where the car can drive itself 99% of the time, but needs to be able to wake someone up if it can't make that determination immediately. That's definitely a design challenge, but it is a stepping stone towards fully automated vehicles. And that's the end of these 6 human-centered design bullet points. There are a number of links at the bottom. Introductory lecture on Lex Friedman's course, Google's guidebook, and some human-centered research at Stanford. And we'll drop into the exercise here, if I can. Yeah, there we go.
You have, if you don't mind, in the upper right corner, a right arrow. Can you click on that so that you have full real estate?
This one?
There you go. Yeah, perfect.
Yeah.
Thank you.
All right, so let's see. So the first question they ask is about Cambodian organization wants to help reduce the significant amounts of plastic waste that pollute the Mekong River system. Which of the following might be an appropriate way to start? Watch people currently addressing problem, navigating existing tools and processes, conduct individual interviews, assemble focus groups. I'm going to run back here and close this other window temporarily because no, I'm not sure. This one may be the one that was causing problems earlier. We'll find out. So reducing plastic waste. After you've answered the question, view the official solution. I mean, the answer here is that all of these people are useful people to talk to, useful actions to do. You always want to get the lay of the land of the problem before really diving in with a solution. I believe in this section, each one of these questions, if I recall correctly, had to do with each one of them had one of the 6 bullets that they had in the last section. So the second question, detecting breast cancer. Now we're going to be asking if AI will add value to a potential solution. And this is definitely a canonical use case for AI, right? The 4 points that they made in this section in the last time was, is this a solution that will provide real value to people? Absolutely, if it saves lives and detects disease earlier. Another question was, is this something that AI can do better than humans? That is questionable. Certainly, top radiologists should be able to read X-rays and other imaging, or sorry, this is cells on tissue slides. Certainly, the experts can read the information easier, probably, than an AI, but they can't do as many of them per unit time. They tire, requires an expert eye, it's repetitive. It's certainly a case where AI could be leveraged as a second opinion, at the very least, to filter out cases and direct the expert's attention only to those cases where the answer is less obvious. And it does say, due to the complexity of your work, you have not found rule-based systems to be capable of adding value, which was the 4th point that they had on the other slide. So, right, This question is kind of an obvious yes. Third one, flagging suspicious activity. A bank is using AI to flag suspicious international money transfers for money laundering, anti-terrorist financing, or sanctions concerns. Though the system has proven more effective than the bank's current processes, it still does frequently flag legitimate transactions for review. So what are some potential harms that the system could cause? How can the bank reduce the impacts of these potential harms? And the most obvious harm, I think, from this example is that it could learn from its training data that transfers involving certain demographic groups have been labeled more often as suspicious in the past, and it may be more likely to flag legitimate transactions from people falling into those groups, which is an instance of bias caused by demographic inequalities within the training data. And what might you do to reduce the impacts of these potential harms? You can refine your algorithm in certain parts of the input space. Just try to do better on these groups. Somehow you can use also strategies such as boosting type techniques to weight your training data a little bit differently in an attempt to debias it. And another really important thing that you want to do is have ongoing human in the loop. Always have specialists on your review team available and ready to focus on this issue when it crops up. Have someone who's well aware of this particular issue and how it affects these groups of people. The fourth question, prototyping a chatbot. During an ongoing pandemic outbreak, a country's public health agency is facing a large volume of phone calls and emails from people looking for information. The agency determines that an AI-powered chatbot answering pandemic-related questions will help people get the information they want quickly. How should the agency start prototyping the chatbot? So there's really two choices given: build out the AI solution before testing it, or build a non-AI prototype quickly and start testing it. And the correct answer is the second one. You want to build your non-AI prototype. Don't build the chatbot speech generation model. Build a system that's going to look like that interface and maybe have humans behind the system while testing it with a diverse group of potential users. Get feedback on what the system, how they interact with that system, with people pretending to be the chatbot, so that you can understand how they might best benefit from your chatbot in the future.
Yeah, that will help you also get to know your audience better and your users better. So definitely go with a simpler approach first.
Kill two birds with one stone.
Yeah.
Customer research. Number 5, detecting misinformation. You have a social media platform planning to deploy a new AI system, flagging and remove social media messages that contain misinformation. The system has proven effective in tests. It sometimes flags non-objectionable content as misinformation. What are some ways in which a social media platform could allow someone whose message has been flagged to contest the misinformation designation? Interestingly, they don't identify what social media platform they're talking about here. I guess we can leave it to the imagination of the person answering the question. So the question now is, what are some ways in which a social media platform could allow someone to contest the misinfo designation? And I think the obvious thing is to allow an appeal, and if you have a source that can back up your claimed information, then have a mechanism that allows people to quickly appeal that and get reasonable judgments in a short amount of time. As a somewhat analogous example, YouTube has a somewhat robust system for content creators to flag other people's work for copyright infringements and that sort of thing. And there's a whole procedure for people to either contest those claims or take down or alter their videos accordingly. I think one should also, if you are designing such a misinformation detector for a social media platform, or if you are a government official or any other stakeholder tasked with setting limits, determining what should count as misinformation or not, do recognize that it's a very slippery slope regarding the First Amendment versus protecting the public from misinformation. And the sixth question here, improving autonomous vehicles. What are some of the ways to improve the safety of autonomous vehicles? Incorporate safety features, test the system, hire a red team. And the answer is all of the above. Also, you want to have a mechanism for alerting the operator or whoever's in the vehicle at the time, and some mechanism for people who has used or observed the system to provide feedback that you can go through to improve your system in the future. Any questions on Unit 2, or should we move on to identification of bias?
That human in the loop concept is very important to me, so this is another use case. Liana is talking about disinformation. I'm not sure what you mean by that, Liana.
Oh, just we were talking about misinformation. Disinformation comes with its challenges because you're trying to identify intent, which, how can we ever have AI that can actually identify intent to misinform?
Yeah, that's a really good point, and it's only different by one letter, but misinformation and disinformation are two different things that perhaps should be treated differently. It's also so difficult to solve these problems because sarcasm is such a natural aspect of human discourse that really needs to be accessible for humans to gain value from communicating on the internet. However,
the whole of Australia would be censored. The whole of Australia would be censored.
I feel like
the whole of Australia was censored for a few days.
I feel like another challenge with misinformation and disinformation is like defining like ground truth. Like some people like legitimately believe, say, misinformation or disinformation, and like, but you then assume that, well, the platform then knows what's true and not. And so, like, I mean, I'm not saying I think like conspiracy theories are true, but my point is like it then puts these companies in the position of like defining, establishing some like ground truth when maybe they're not. Maybe that's a little bit hard. That's a tall order to ask AI to do, if that makes sense.
Not only is it a tall order to ask AI to do, but are the AI giants the people that you want as the arbiters of those questions?
Yeah, it's not like we have this dictionary of all of the ground truth facts in the world. And we now live in this world where the term alternative facts exists, which is an interesting series of words in itself. But yeah, very interesting.
Yeah, it does highlight the large number of challenges that we face, though, and how AI itself has, in some ways, it's the macro scale version of this same set of issues that we're discussing here, how AI itself has wrought various challenges upon us that were probably unintended by its developers, I hope.
You hope, yeah.
So we'll move on to identification of bias in AI. Machine learning has the potential to improve lives, but it can also be a source of harm. As we know, machine learning applications have been shown to discriminate against individuals on a variety of bases: race, sex, religion, socioeconomic status, and many other categories. In this tutorial, we'll speak about bias. We'll cover 6 different types of bias. We'll note that we are talking about a different type of bias than the one that is contrasted versus variance and overfitting. That's a different topic here.
Mm-hmm.
So this little bullet here is bias is complex. There's a lot of different sources of bias, and you really want to be aware of all the different places within your data science or data product pipeline anywhere that bias is likely to occur. Six types of bias. So it is a good thing to classify these biases into 6 types just to enable one to more readily be able to detect them, or just to have that framework for thinking about them regarding ML projects. And also, with a common vocabulary, you can have better conversations about how to mitigate those things. So historical bias is the first one, and this has to do with occurring when the state of the world in which the data was generated is flawed. And the example provided here is that a very small fraction of Fortune 500 CEOs today are women. Research has shown that companies with female CEOs or CFOs are generally more profitable than companies with men in the same position, suggesting that women are held to higher standards than men. In order to fix this, we might consider removing human input. This can prove unproductive if data from past hiring decisions is used to train the model. So what you're really trying to look out for here is training a model based on historical data can replicate undesirable things that occurred in the past due to possibly cultural reasons, any number of reasons, but something that you don't necessarily want to perpetuate going forward. So one other good example of where historical bias could come into play is in natural language or language models. We know that the use of languages and language and terms can evolve over time, and terms which were considered normative or at the very least not offensive in one era could be viewed very differently a few years down the line. So it's important that we not train our chatbots based on different ways of speaking that have become unacceptable. The second source of bias is representation bias. And this is another form of sampling bias, but essentially this is where you are training a model and you're selecting a different sample set than what you are intending the model to serve. The example provided here is smartphone apps. If you are collecting data in the USA and you want a general sample of the population, using smartphones may not give you a very good age distribution. You'll underrepresent individuals over the age of 65. and that can have consequences for your decisions regarding a city transportation system, for instance. On the other hand, we know that landline sampling can produce the opposite results.
Isn't
So
that
a
a famous,
third,
sorry,
oh, go ahead.
isn't that a famous issue with election back in the, was it 40s or 50s, that that Gallup overcame? Basically, they were asking people over the phone, who is your favorite president, who would you vote for? But by doing that, you're only basically calling people who had a phone. And this was in the 50s, I guess. So I guess only rich people. And Gallup is like, that's not right. And he did, I think, a mail-based approach, and he got more accurate results. And that's how he became famous.
Yeah, that's a very interesting story and a great example of this effect. Our third bias source is measurement bias. You can get measurement bias when the data accuracy of your data varies across groups. This can happen if you're working with proxy variables in particular. So the example they give here is, suppose you're trying to identify high-risk patients in a hospital, and you are using past costs to predict who might have high risks in the future. And if you have some subset of your population that, for a variety of reasons, is less likely to come in for maintenance or preventative type visits, then their lower costs to date may not be an appropriate indicator of future risks. The danger here was in using the proxy of current low dollar costs, we'll say, for risk. Then you are introducing this source of bias because it's not being accumulated the same way for different groups based on those groups' behaviors. You might imagine a similar example if you're using some kind of broken windows theory of policing, right? If you're trying to predict the incidence of violent crime in a particular jurisdiction based on the number of reports of small crimes, that may not be a good indicator, especially if certain zip codes have much less trust in the police than others and are less likely to want to involve police in local matters. Our fourth example is aggregation bias. So this is one that you can get when groups are inappropriately combined, resulting in a model that doesn't work well for either group, or maybe it only works well for a group where you do have a lot of people. The example shown here is that we have a group with higher rates of diabetes, Hispanic Americans having higher rates of diabetes and diabetes-related complications than non-Hispanic whites. If building AI to diagnose or monitor diabetes, it is important to make the system sensitive to these differences by either including ethnicity as a feature or building separate models for different ethnic groups. Now this is an interesting recommendation and can solve the problem, but I think it's also important to note that you can introduce other dangers by attempting to build separate models for different groups. So this is all part of the conversation, but you do want to be aware of the potential downsides of including these things directly as features. I think we'll see that in the section 4 on model fairness as well. Evaluation bias. This is when you evaluate a model if the data that you're using to evaluate your model on differs in any way from the intended use case, then you can get evaluation bias. In some sense, when you are dealing with a time series forecasting problem, there is some inevitable evaluation bias because you can only evaluate on data that's already occurred and you're intended to use the model in the future when the data distribution may drift. Mm-hmm. Another example they give here is a facial analysis benchmark data set, which is primarily composed, or was primarily composed, of lighter skin subjects, and the commercial gender classification AI showed state-of-the-art performance on those benchmarks, but then when deployed experienced disproportionately high error rates with people who looked differently than those people in the data set. So the lesson there is to really think about your use case and try to get your validation set as close to your real use case as possible. And deployment bias. This is when you have when your model is, the problem your model is intending to solve is different from the way it's actually used. If you're solving one problem, but your users are using it a completely different way, then you might get undesirable results. The example here is a criminal justice system that is using predictive models to predict the likelihood of recidivism. And these predictions are not designed to be used by judges to determine appropriate punishments at the time of sentencing, but it's conceivable that they could end up being used that way. So just another thing to be aware of. Now, one thing that buried at the bottom of this slide actually is a really great visualization, and it comes from this paper. Let me move the window down so I can see where this Framework for Understanding Unintended Consequences of Machine Learning by Harini Suresh and John V. Guttag at MIT. And we'll get a view of the diagram right here. But essentially, it's a way of visualizing all 6 of these sources of bias, showing where they occur typically within your pipeline. And by knowing this framework and understanding where these things can happen, it allows you to really think about the sources of bias and take whatever steps you deem are appropriate to mitigate them.
I really like this diagram, because usually you only see projects referring to historical bias, bias in the data itself. But this introduces some interesting other concepts that I find that super useful.
Yeah, I'd say historical bias and representation bias, I guess, are big ones. Maybe you wrap them up under the umbrella of sampling bias, but it's easy to forget that these other sources of bias can be very important as well. So we'll jump into the exercise, which this is the one with the jigsaw puzzle, isn't it?
Yeah.
So in 2019, Kaggle held a competition on the jigsaw unintended bias in toxicity. I guess we have a link here we can click on. The purpose of this competition, I think it was just a binary classification task, right? Detect toxic or not toxic.
Yep.
And one is supposed to determine, and where toxic is defined as, they define it, yeah, anything rude, disrespectful, or otherwise likely to make someone leave a discussion. So there are any number of comments and other terms that could be viewed as toxic in an AI system, and one can imagine many considerations that should go into designing a classifier for this kind of thing. In this course, we're not really talking about the model itself so much, really more about its implications. But it is interesting to see this example throughout this notebook here. A couple of setup cells here. What they do is create this model that's going to do, I think it was a kind of a bag of words type model where it's just looking for certain terms, and then depending on the average toxicity associated with each of the words that it finds in the sentence, it determines whether to call it toxic or not. So the first exercise here is you try out the model, and you can just type in different items here and get certain results. I guess I can see if I can train this anew. And if you do a sentence such as the example that they showed there, or apples are stupid, or you are stupid, or using the word stupid in the sentence, you're going to get it rated as toxic by the classifier. Let's see.
You scroll up, you're going to see some information about the data cell itself. So the first cell ran successfully.
Mm-hmm. Yeah, it looks like the first cell is done, so I think it is functioning. And the training is done. 93% of the comments in the test data are classified correctly, or at least they match whatever labels someone put on them.
Mm-hmm.
And then you're supposed to try out the model by just typing in their variety of sentences here. And it's looking for words, and so if it sees the word stupid in the sentence, it says it's toxic. So it doesn't matter if you use that one or you are not stupid. It's still going to call it toxic just based on the appearance of the word stupid in the comment. So not the oh, what was that?
I wonder if the word toxic is toxic. I didn't try it.
I did not try that one.
Oh, all right. Very good.
Britney Spears is safe.
And for the record, apples are awesome.
Let's see. So then they print out what is the list of the 10 most toxic words.
This was an interesting one.
Yeah, I did think this was interesting. First of all, there's really only, so they're sorted in, the most toxic word here is at the bottom. So the bottom 5 words really only contain 2 different words. But these words here, it's not difficult to imagine that the use of any one of these words is a reasonable indicator that a comment is more likely to be toxic than if it doesn't include one of these words. And I believe that's the first question or second question they ask. Given the nature of the approach, bag of words, none of these 10 words seem unreasonable as indicators of toxicity. So this one was interesting begin by running the code cell as is to classify the comment, I have a Christian friend, not toxic. You should see it was classified as not toxic, but then you see that there's a unfortunate behavior here that it classifies I have a Muslim friend as toxic. Now, one could speculate on why the training set led it to make that determination, but clearly this is undesirable behavior for most applications, one would hope. And you'll see similar results here. If you try these two sentences, you'll find that the first is labeled not toxic and the second is labeled toxic. Again, you can try out a number of other things here, but you just see certain biases that clearly came into this data set from somewhere. Do you see any potential signs? Yeah, pretty obvious. So then we're going to step away from the jigsaw competition data and look at the set where you're looking at a data set of online comments. Comments referring to Islam are more likely to be called toxic than comments referring to other religions, and I guess they're speculating here that this is because that online community is Islamophobic. I don't know if that's a statement on the global online community writ large, or if that's just this data set. I'm not sure what that refers to. But in any case, they want you to classify which type of bias that can introduce to your model. I think they say historical data. I thought it was maybe a combination of historical and representation bias, because certainly if your data set were biased to, or if the user base that was generating the comments happened to be more Islamophobic than the globe as a whole, then that would lead to this behavior. So that seems like could be representation bias as well.
Is that, I don't know, is that the reason why this community closed? Like I was reading online.
What community?
Common creative community, basically where the data source, the data source that this puzzle came from, or I think the community was about to shut down, and just before it shut down, I think that the Kaggle data set evolved. I have a link here. I'll show it later.
Yeah, I don't know anything about that.
I find it interesting.
Number 6, test your understanding, part 2. So continuing with the same scenario, trying to train a model but to classify comments as toxic. What happens if you take comments that are not in English and translate them to English with a separate tool, then treat all posts as if they were originally expressed in English? What type of bias will your model suffer from? I think I answered aggregation bias. If you're combining certainly comments that are written in English versus comments that are written in other languages are likely to have been produced by different groups of people that have real differences in their own backgrounds, and therefore combining them with no indication of where they came from could produce aggregation bias and hurt model performance. But they also point out, I think down here, that there's measurement bias as well, since the non-English comments are, especially if you're using an automated translator, they're not necessarily likely to be perfectly translated, so they could be a little bit further from the speaker's intent than the English comments if processed in this fashion. Test your understanding, part 3. We'll continue with the same hypothetical scenario. We're trying to train a model to identify or classify online comments as toxic. and we're looking at data from the UK, and you're evaluating its performance with another data set, also from the UK, and it gets great performance, and then you deploy it for a company based in Australia, and it does not perform well because of differences between British and Australian English, and maybe a lack of sarcasm detection. I don't know. What types of bias does this model suffer from? And the answer here is evaluation bias, for sure, and deployment bias, and you also have some representation bias if you're building it to serve users in Australia, but you're training it with somebody else.
Interesting.
And many more links at the bottom of this page. Anything interesting from these? I don't think I looked at these ones.
I mean, the competition, yeah, that was 2 years ago. There's a lot of notebooks, great notebooks there. Some of them use simple data science approaches. Some of them use simple sequence models, and other ones use like transformer-based models to classify text as toxic or not toxic. It is something we can revisit in the future.
And anything from the chat, or anybody want to join the conversation?
I think we're good. I shared that link that I mentioned about the civil comments shutting down. I don't know if it was related to this or not. It's just I noticed that the data set for this toxicity classification task came from there.
By the way, I'll drop this the link to this paper that has this great diagram in it. Okay. And I will stop sharing screen so that George can move us into
I have a comment.
Oh, sure, Kathleen.
So much of what you just went through, Robert, was like it would be applied to anything, any kind of data analysis, and you're not getting what you're trying to get. You're getting something wrong. There's whether it's an ethical thing is whether it harms specific people or specific groups. I mean, it's just an observation, but all the things in the beginning about what you would want to do before you start a project or before you employ a project, you'd want to do that with any product. I think you mentioned that, Robert, in the beginning too. So there's something subtly different about whether it's an AI ethics problem. That's all.
No, I think that's very important to keep in mind. We're really just viewing ethical considerations that should be applied to any project and trying to see where those considerations, how to make those considerations a little bit more specific to an AI project. But as you've pointed out, I mean, it's really the same basic list of concerns. I don't think that this course would be too terribly different if it were written about software development for 30 years ago or something.
Yeah, I mean, you just don't want to get the wrong answer, but then when is the wrong answer really bad for people? One thing that was, I think, was specific to deep learning or a complex AI model was in the very beginning, it said something about, well, using a simpler approach. If a simpler approach used the black box issue with the deep learning, where you don't really know what's going on inside, so you can't pick it apart so easily as you might with another model and find out where your problems lie.
Yeah, although I would contend that same logic can apply even when you don't have so much of a black box. If your new and improved solution isn't actually improved, then maybe there's no point in applying it. Maybe that's not so much an ethical consideration. But I think it really is. There's very little in what we see in this course that is really specific to AI.
Mm-hmm.
But it's important for people in AI because we can have outsized impacts on a wide range of people without even noticing it. It may be more important for AI engineers to have these considerations in mind than for people in many other fields.
Maybe.
Awesome. Thank you, Robert. Thanks, everyone, for participating.
Here's a question. It's slightly on a tangent, but there's been more talk about AI ethics recently, and is that because people haven't really thought about ethics in AI, like in combination before? Is it because like data science as a field has kind of ignored it? Like, why is this now a new talk when perhaps, as we were just discussing, like these ideas have been around, they're not new?
I think there's a lot of reasons for that, but I think the general population is waking up to how AI can and will change their lives, and it's just that much more critical to have these discussions now, maybe than people thought it was, for all these other issues that we've faced in the past. I think in reaction to that, you also have a lot of actions that are done in ways that can be perceived as action for the purpose of making it look like you're taking an action without actually addressing some of the underlying issues. There's a lot of discussion about tech companies that may be virtue signaling towards inclusiveness without really being as inclusive as they think they're being. That in many cases that may not be that may not be for lack of trying, right? It may just be that the companies don't understand yet everything that they need to do. But I think there's a lot of perception that needs to be fought there as well.
Yeah.
Be really curious to hear others' thoughts on that.
Yeah, for me, it's the scale, right? I mean, AI has been used in so many, and the speed of it and the applicability of it, so many applications that, it's like a software development process that's moving so fast that people need to slow down and really think about the consequences. So it's affecting decisions, it's affecting people's lives, it's affecting people's, trajectory. So anything that impacts, human lives, absolutely. When you take a step back and revisit as a society, is that the right thing to do, and how is it done, and if it's done wrong, who is responsible, and can we take a deeper look of, can we learn from it, can we make sure it doesn't happen again? Think about it, like the early accidents in the self-driving car industry, and so forth. So
I think one of the reasons why this may be coming up now is that there is a diversity of voices. While it's not solved yet. There's not enough representation of diverse groups, but there are a lot more than there ever were. Technology has always been moving quickly, for, at least in the last 50 years or however many years. And you didn't have people in there to say, hey, wait, what's this doing to this group? What's it doing to that group? Why are seatbelts, why are airbags made for, designed for men? Why are heart attacks studied for men? Because there weren't enough women in there around to say, this is wrong or misguided. And now there are more diverse voices.
Like there's a profitability factor in it too. Maybe not so much with airbags and cars, but in the social media realm, how a company's incentivized. They're incentivized to have in a lot of ways to have these toxic engagements and those virtual signaling. So the scalability of their wealth exploded as well, as far as the question as to why now. As soon as anyone is making insane amounts of money and they're incentivized to keep doing what they're doing, because, you know, why wouldn't they until there's public pressure to not do it? I think that's a really hard problem to solve without some sort of governing body.
Yeah, and I think a lot of times AI comes under fire for being an accelerator of inequalities in wealth distribution, which it absolutely has been, but I think it's a mistake to attribute that to blame the designers, so to speak. Like, I think there's a lot of technological progress that can be made, but technology and techies are not the only people that need to make progress in this area, right? We need to design social systems that are able to handle the coming automation.
Absolutely. I think it's too easy to point to an algorithm and say it's the algorithm's fault. That's too easy of a cop out.
Right. But I think the fact that people are being automated out of jobs it's controversial, because all of a sudden um they're facing real hardships. Like, these are real concerns, and this is something that we need to address, not in the tech community, but as a society at large. How do we don't necessarily want, if an AI is capable of doing some really boring job, do we really want some person to be doing that if an AI could do it for them? I mean, maybe the person could be doing something else that's a more um, fulfilling use of their own time. We just need to make sure that we can get to this transition in a way that doesn't, um, in a way that ensures that people can continue to live as they did before, even in the face of this changing job environment. Right? We can't. We need to design the right safety nets that don't.
Robert, I think one interesting thing there is this challenge isn't a new one, and it's not really like AI specific at all. It's really more general. So like when you have like technological disruption, you see in economic history that, you have more efficiency gains and now like there's more productivity, but you've just thrown a bunch of, I don't know, women sewing clothes out of jobs. And so now what are they supposed to do? And so it's a fascinating area of economics. Like how do you retrain, reskill workers for like a new economy? And it's, an old problem, and I don't think humanity has solved it. And I going back to the original question, I think it also isn't necessarily related to AI ethics, because I don't think it's a problem that like, I mean, it is if it makes human lives worse off, then yeah, I think that's an ethical consideration. But if it makes lives better, or say like in a business context, like it has efficiency gains and it frees up humans to do more value add, so humans are then more productive, then I would say that has more value. Yeah.
Right. The answer to the sewing machine putting so many people out of jobs was not to stop development of the sewing machine.
Or the cotton gin.
So it's fascinating to hear all different thoughts. I'm not, machine learning expert or AI expert, but my thought automatically went to, maybe because I haven't done a whole lot, my thought automatically went to, there's a Netflix movie called The Social Dilemma. And so I really like Catherine's point of view, is maybe it's not just AI, and because in that case, is it really ethics about social media, or is it ethics about AI, or it's just ethic overall? So I'm really interested in this topic, but when I came in, I was looking for some sort of guiding principle. And I don't know. So I don't know how many of you seen that documentary, and it really made me think how, you know, there's a debate whether it really contribute as much as the documentary said, that affecting even election, and not to mention it make the society very much divided. And I can tell you just around my groups of friends, very, very, very divided. So anyway, that's my thought. And I didn't go to the automation part. It's now you guys mentioned it, that seems very natural. You know, people lose job because of AI development. But yeah, so.
Something I find interesting, to May's point with having that guiding principle, is that it's such a complex issue that ties into, like I said, socioeconomics, and like it's not just an AI problem, it's not just an ethics problem, and we're very, very much dealing in the gray, where it's not a binary problem. So it's even hard to get clear on what a guiding principle is, because it's hard to even just nail down what are all the groups and what are all the industries affected by this. And then on top of that, the legislative side of it, the government, the political side of it, as well as the private sector side of it.
Yeah, it's really hard to think of sectors within society that will not be greatly affected by AI in some way or other.
Yeah.
I haven't seen that Social Dilemma show. I might watch it. Is it the one related to Facebook, or is it something else?
All of it. So it's you know, Facebook, Instagram, and was it TikTok? I'm not in that generation, so I heard about TikTok and all that.
I'll share my screen and share something. I don't know if you watched this show called Silicon Valley, but in season 6, episode 5, they talk about ethics, which is technology ethics, and they talk about similar, like how companies should be ethical and should do this and should do that. And I'm not going to spoil it for you, but it's a fun approach to ethics, into technology in general, not just AI. So I found that really interesting and really funny. Cool. Thank you, Robert. I love the discussion. Thank you, everyone, for participating. So we have a couple more lessons or a couple more topics to cover quickly, and I found the exercise as well really useful, so I'll try my best to cover them together. So fairness is the next topic that this course introduced, and really looking at fairness in general, you know, machine learning, not just AI, so or deep learning. So this course talks a little bit about 4 fairness criteria, and I think this comes from a paper as well that I'm going to post soon. One of the fairness criteria is what is called a demographic parity or statistical parity, where basically if you're looking at 2 different groups, and there's a specific example here. For example, a nonprofit is organizing an international conference, and there's 20,000 people that have signed up to attend. And the organizers want to pick up random 100 attendees to give a talk. We know that the attendees, 50% of them are men, 50% of them are women. So they want to make sure that the model they designed to pick these 100 attendees to give a talk at the conference is representative of the audience that is actually attending the conference. So we want to make sure basically that the population that the model is serving, those statistics are also maintained when the model does predictions as well. I'm going to look at some more examples, more concrete examples in the exercise. Another one is this equal opportunity fairness.
George?
Yep.
Can you increase the font just a little bit?
Oh, my bad. Sorry.
Thanks.
Absolutely. Another one is this equal opportunity fairness, where you basically want to look at metrics like we've seen in the past related to confusion metrics, metrics like true positive rate or sensitivity of the model. We want to make sure that that true positive rate is the same across different groups. So if we have two different groups, we want to make sure that when our model detects a true positive case, that proportion is the same for one group versus the other. So one example here is that a doctor is using a tool to identify patients that need extra care. And this again is used only to supplement the doctor's practice. It is designed to have this high or true positive rate for each demographic group, based on, again, sex, race, religion, and so forth, demographics, and so forth. Another one is this equal accuracy metric for each group. So the percentage of correct classifications should be the same for each group. So if for one group the model is 90% accurate, it should be 90% accurate for other groups as well. And the example here is that you have a bank that uses a model to approve people for a loan. And the model is designed to be equally accurate for each demographic group. This way, the bank avoids approving people who should be rejected. That way, that'll be financially damaging, both for the bank and the applicant, as well as should avoid rejecting people who should be approved. That way, both the person is losing an opportunity to be funded, as well as the bank revenue income. And the other one, the last one, is this group unaware, or fairness through unawareness, where you're basically removing all group membership information from the data set. So for example, if you remove data, if you remove gender from a data set, then you're hoping to make the model fair in terms of different gender groups. So if there's no gender information at all, then hopefully your model doesn't pick on gender as one feature and doesn't discriminate one gender versus the other. You can do this for other features or other group identities as well. So one example here is, for example, with zip code related information. So if you're doing some kind of analysis where maybe income, you want to be income unaware, but somehow you, or in this case it's race, but somehow you preserve zip code. In many cases throughout the country, there's a strong correlation of zip code and race or income. So you also need to strip out that information as well if you want to make sure that your model is group unaware. Great. So then this matrix really put things together. I mean, this is a generic one, but we'll look at a very specific one soon, where we have this confusion matrix. Again, on the rows, we have the source of truth, what is true. And in this case, we're looking at a confusion matrix for I think any model. This is not specific to a specific application. So the true state is, let's say, deny, let's say false. And in the columns, we have what our model is predicting, deny or approve. And if both of us match, so the truth is deny and our model predicts deny, then these are people who should have been denied and are denied by the model. If both of us are, if the state is true and also our model predicts true or approve, then these are the people who should have been approved and are approved by the model. I think this language is more appropriate for that loan example. Now, let's say the state, the source of truth is true, approved, but our model is denying them for whatever reason. Then this is the population or the people who should have been approved but are denied by our model. Okay, that's the intersection of the rows, which is the true state, and the column, which is what our model is outputting. So the off-diagonal items, and the opposite as well, where the truth is we should deny people, but our model is approving them. So these are people as well that ideally we should minimize. So one specific example here, again, you want the diagonal entries to be as high as possible, and you want the off-diagonal to be as low as possible. In this very simple confusion matrix example. Cool. We're going to look at one very specific example from 20 people. Let's say we have, that's our data set. We will equally split them into two groups. Group A has 10 people and Group B has 10 people. Then we're going to look at some confusion matrices, and we're going to look at how do these fairness metrics look like. So let's say, for example, that our model produces this output or this confusion matrix for Group A and produces this confusion matrix for Group B. So if we're going to look at demographic parity, we basically want to look at the total population that is approved, regardless if they should or should not be approved. So basically, we want to look at the approved column for our model. So we looked at for Group A and Group B. For Group A, we have 5 plus 2, 7 people. And for Group B, we have 4 plus 3, 7 people. So we have 14 people overall that are being approved, and 7 and 7, they're split equally between Group A and Group B. If for whatever reason we're approving more people in Group A versus Group B, then would have we wouldn't have demographic parity, basically. Wouldn't be fair in this demographic parity metric. In the second one, which is the equal opportunity one, we're looking at the true positive rate. Let's say this is another model. This is another confusion matrix for Group A, and this is another outcome for Group B. So the true positive rate means true positives, which is 4, divided by 4 plus 2, which is the positives regardless if our model agrees or not. So in this case, we have 4/6 or 66% true positive rate. In this Group B, we have 2/2 plus 1, and again, 66%. So with respect to the equal opportunity metric, we're being fair as well. We're not discriminating Group A versus Group B. The other one, which is looking at the accuracy, is looking at the diagonal items here. If we basically we want to count, we want to measure how accurate we are, basically how many, the true positive and the true negatives for each group, how does that relate? So we're looking at the true negatives, 2, true positives, 6 plus 2 over all entries, which is 10. That's about 80%, or exactly 80% for Group A. And then 4 plus 4, 8 over 10. Again, that's again 80%. So we are being equally accurate here as well. We don't have a specific example for Group Unaware. I think the exercise has one, and we can look at it as well. And I find this interesting that none of the examples above satisfy more than one type of fairness. And they mentioned this Impossibility Theorem of machine fairness, where you basically have to pick one. And then this is where the ethics part comes, where we didn't have a discussion, okay, which metric do we want to design our AI model so that we are accurate about? Are we interested more about equal accuracy? Are we interested more about equal opportunity, or this demographic parity metric? Or maybe some other metric, or maybe that we haven't covered. Again, this requires a lot of discussion. It's not a straightforward answer. Cool, there are some links here. Maybe in the end I can go through them. This What If tool as well is a nice, interesting tool from Google ML Fairness team. And this blog post was also very interesting. I think the exercise will cover, let me zoom a little bit more for us. We'll answer some of our, we'll make this concept more concrete. So in this case, we are looking at a synthetic data set. This is not a real data set of credit card applicants. And let's see how that data set looks like. So reading data from the CSV file, we are dropping the target, which is basically if a transaction was approved or not. We are saving that in our Y variable target. And we are doing an 80-20% split into training and test set. I think this has several thousands records, if I'm not mistaken. So nothing fancy, we're just looking at different data. And let's see how that data looks like. Let's look at a few entries from the training set. How many children does a person or family have? Which group they belong to? And we only have two groups here, 0 or 1. What is their income? If they own a car or not, and if they own a house or not. And just I want to take a deeper look at the data. So we have about 500K data overall. About 250K of them belong to group 0 and 250K belong to group 1. So I want to make sure that was balanced in terms of groups. And then that 80-20% split gave us 400K and 100K in terms of training and testing data sets. So yeah, the income, number of children, whether the applicant owns a car or owns a home. 1 is true, 0 is false. And when we'll look at, when we will evaluate fairness, we'll check the different fairness criteria across these two different groups. So the group column breaks into two groups, 0 and 1. And again, this could be anything. This is very generic for our example. 1 could be, for example, different races, ethnicities, or gender groups. And in which case, you know, for example, 0 could be non-Hispanic user, 1 could be Hispanic user. Or, you know, races, you could have more than 2, you know, and so forth. Cool. We'll work with some interesting libraries. I think we've seen this in the past in our machine learning journey. We'll look at sklearn, the tree. We'll use a basic decision tree classifier here. Also look at a confusion matrix, and we'll display it as well. So we are looking at a decision tree of maximum depth 3. We want to make sure we avoid overfitting, so we want to stop the depth at a given level. We'll fit our training and X and Y data sets here, and also the prediction on our test data set. This is just some code to plot the confusion matrix and plot some interesting stats in terms of how many applicants were totally approved, what is the overall accuracy, and so forth. So when we look at the entire data set, the 400K records again, about 38,000 of them were approved. And then if we want to break it down by group, 20% of them belong to group A and 79% of them belong to group B. So immediately we see that something is off here, right? We see discrepancies when we look at approvals for different groups. If we look at overall accuracy, the true positive and true negatives, that's 94%, which is pretty good. And then when we break it down by group, it's more or less the same, 95-94%. So I think we're doing well here. And then when we look at the true positive rate, group A has about 77% accuracy, and group B has 98% accuracy. So definitely there's room for improvement there. And this is a confusion matrix for group A. And this is a confusion matrix for group B. So looking at the different metrics here, we can see that we approved 38,000 people. 8,000 of them belong to group A, 30,000 to group B. So there's definitely, we're not being fair there. And I think this is just some calculations. I think later on we're going to evaluate each metric here. I added one step here to just visualize the tree. And I didn't realize that the notebook itself also visualizes it. So I'm looking at these different features: number of children, group, income, on car, on housing. And we're looking at this level 3 tree. the most important feature is income. And this decision tree that we trained is looking at each record. If that record has income less than $80,000, that is true, it goes to the left sub branch. If it's false, it goes to the right sub branch. We start with 400,000 records. That's the X train size. And when we look at the target, which is approved or not approved, 245,000 of them belong to, I think, deny, and 154 belong to approve. So then if we follow this tree here, and you can see, again, the second level is also based on income. And sorry, this I didn't mention, this Gini is basically a measure of the uncertainty of our model. It's also information theoretic related. So the higher this metric is, the more uncertain the model is about its classification. So the deeper, as you'll see, will go in the tree, the lower this uncertainty will become. So again, let's follow this path. We have income less than 80. We have income less than 70. If it's true, we go left. If it's false, we go right. Let's say we are between 70 and 80. Let's say we're 75. Now the next feature that this model is looking at is group. So this is something that maybe we don't want to, right? Because basically now we're making a decision based if we belong in one group versus the other. So if we belong in group 0, we go left, we are denied. If we belong to group 1, we are approved. So this is clearly a decision we're making here based on group. So then looking at demographic parity, equal accuracy, and equal opportunity, I'm just plotting them here. This for the metrics again. So let's look at demographic parity. So demographic parity means I need to sum up the columns here, 7,500 and 1,900 and 28,000. You see definitely a difference there. So I also normalize them. So that's a difference of 20%. We also see it here. Of approvals come from group A and 80% of them come from group B. So we are not being fair in terms of this demographic parity metric. When we're looking at equal opportunity, we want to look at so if we go back to our chart here, equal opportunity means the true positive rate over the sum of the rows. So the true positive rate over the sum of the rows here and here, and that is 77% and 98%. So we're definitely not being fair there as well. And the last one is looking at the equal accuracy, which is looking basically just at the diagonal entries. That is closer to what it should be. So yep, all of the fairness criteria are unfairly biased in favor of group B. So almost 80% of applicants from group B are so yeah, 80% of them are from group B. We started our data set, remember, has equal number of applicants from group A and group B. If we wanted to be demographic parity fair, then our model should have approved equal numbers of applicants from each group. Cool. And this is the visualization that the notebook has. So a very basic one based on income. This is the part that introduces this unfairness, I think, for our model. We're specifically picking, making a decision based on group, as well as some other characteristics that we'll see how group and income are related. Yeah, that's the journey path that I explained on how you traverse that tree. Can you explain one source of unfairness? So I think this one is picking a specific example. Let's say somebody has income between 71,000 and 88,000, and that's the same journey that we took. So we're between 70 and 80, we're here. And then the next one is, the next decision we're making is based on group. So the model approves applicants from group B and denies applicants from group A. Something that I wanted to look at was maybe average income for each group, and I saw that for group A, the average income is 64,000 versus group B is 80,000. So there's a little bit of implicit here, unequal distribution of income, or average income across groups. This is just a reminder. Then what if we removed the group field altogether? How would our performance be? So we remove the field group altogether, we retrain our classifier depth 3, and then we'll look at fairness again. Let's see how that performs. Total approvals 36,000, 31% of them are in group A, 68% of them are in group B. Overall accuracy, I think, dropped a little bit. I have a specific visualization for us right here. Yep, there it is. So when we had the group field, these are the metrics, and I also plotted this difference here to show you that we are favoring group B significantly here. So I'm doing the difference between a metric of group A with group B. So we're at -0.5, -0.2, -0.004. When we remove the group feature, the demographic parity improves a little bit, but still is heavily biased on group B. Equal opportunity improves significantly. We're now at 93.86 versus 77.98%. And equal accuracy, I don't know, I think it went a little bit in the opposite direction. Notice here that this equal opportunity improved, but also switched direction, which is interesting and I think unintended consequence. So in this case, we were favoring group B. Once we dropped the group, once we became group unaware, we are now favoring group A, which was a very interesting approach. So yeah, how does this compare? The new model is still biased in favor of group B, but not maybe as much. Yeah, it's important to know that the overall accuracy of the model has dropped as well. We're at 92 versus before we were at 94 or 95 here for each group. Then we consider the third model. This time we want to tweak the output of our model in a way that, so we know that our model is biased. Now we want to tweak the output in a way that to overcome this this unequal output. So I think this is an implementation of what is called a group thresholds, and there's a link here that we can visit using that what if tool. So basically what we do is we take our model, which is group unaware. We do a prediction on our test data. But now when we look at the output probabilities, we don't just score them. We don't use them as input to the confusion matrix. We weigh them by this threshold. So we do a decision based on this threshold. So look at the test probabilities, and if the group is 0 and we're above this threshold, then we consider it. And if we are in group 1 and we are above this 99 other threshold, then we consider it. Otherwise, we don't consider it. So basically, we weight our outputs, and let's see how that changes things. So in terms of total approvals, 38,000, more or less the same, but now we're looking at group A and group B. We are definitely in the right path here. We're approving more or less the same number of applicants for each group, and you can see here the confusion metric as well. Our overall accuracy, remember, we're at 95, we went to 94, now we're at 79, dropped significantly. It is still more or less the same for each group, but we dropped significantly as well. And then the sensitivity is went in another direction. We are 100% true positive rate for group A. There's nothing here, nothing here. And we are, sorry, there's nothing here. This is, sorry, group A. and then 63% for group B. So this is me plotting all three now together. So this was the group aware fairness metrics, group unaware, and now this even representation fairness. So we were favoring group B, now we're favoring group A slightly again, 51 versus 48. We were favoring group B, more or less the same. Now we're actually favoring group A. And then equal accuracy, I think, yeah, somewhere in between 79 and 79, which is pretty good. So this one, again, equal representation in terms of demographic parity, but then as you see, things are slightly different for the other metrics. I also wanted to look at the average income as well as car and housing for each group. And this is something that the notebook noticed as well, that group B has significantly higher income average compared to group B. Also has significantly higher car ownership metric as well as housing. So basically, these are the slightly richer applicants with more cars and more homes. Yeah, that's the same observation here. And really the notebook ends with some more links of keeping this in mind and using some other resources as well as this conference that was new to me. But also, yeah, this interesting concept that when you're trying to optimize for one fairness over the other, you might actually have unintended consequences, either in inaccuracy or also the direction, right? When we optimize for something else, we change direction of which group we were favoring unintentionally. Yep. Again, to mitigate bias and make a system fair, we need to look at closer look at every step from data collection to releasing final product to users. Cool. This was an interesting one, especially this journey here. I found that really interesting. Questions, comments?
Can you hear me?
Yes.
Okay, so one challenge I see with this approach is that it seems difficult to get these labels, these ground truth labels of what should have happened. So just getting those labels to understand like the bias of your models, I think is probably like logistically challenging because you have to get these labels from humans, and humans might have, say, unconscious biases that you don't want your model to learn. So then the challenge is quite practical, but like labels are hard to get, and then like getting fair labels, I think, is also hard.
So maybe, yeah, sorry, you don't have only one person evaluating it. Maybe you have like a group of people evaluating each data set, and maybe take like an average. Maybe that will help you mitigate some human biases.
Perhaps. It's still a practical challenge.
Mm-hmm. Yeah, I don't think I've seen a good solution right to the data labeling. I've seen like AI assisted labeling solutions where you have a decently trained model, but then what does that mean? Where you train some labels and use that as label data, but then again, that brings again to question how confident are you that those are the right labels? Okay. Continue. And go to the last concept here.
Message in the chat about reverse engineering AI and about potential other completely other type of negative consequence of AI. I wondered if anybody wanted to say anything further about that.
Reverse engineering AI in terms of identifying why it made a specific prediction or decision?
Reverse engineering AI in terms of, I think, in terms of using AI, like hijacking AI models to use them for something other than what they were designed for, and maybe to hurt people.
So that's, what is that, deployment bias?
No, adversarial ML, I think,
And,
might be what you're getting at.
Where you find, maybe let's say you do image classification, you find what pixels I should change by a little bit so that my class changes from one to the other by very small, minute changes on the input.
Yeah, or I wonder if more practically, like you have these self-driving cars and you happen to find out that if you like put little stickers on stop signs that humans won't notice, but the AI is just thrown off by it.
Mm-hmm.
I just made that up, but like stuff like that is, you know, concerns of it, I guess.
Actually, that's a real case. They did it with the speed limit signs. They basically used some tape to fool AI, and the AI cars took off like in a 30-mile-per-hour zone. They would suddenly zoom up to like 100.
So they hid the number, or they changed the number?
No. They put enough on there to a human would still read it just 30 miles an hour, but the AI was confused by the pattern, and I don't know the details, but it was
It was a weird number, maybe.
I think most humans would also be intelligent enough to not drive so fast that like they are guaranteed to crash their car in a 30-mile-per-hour zone is typically not designed anywhere near what one could drive 100.
Yeah.
So presumably an AI could be taught to ignore speed limits similarly, right? Like they certainly should recognize icy conditions and slow down accordingly as well.
Or use multiple data sources, like maybe they can use maps, and the maps themselves have hard-coded speed limits as a plan B.
Then you're relying on data quality, which,
Sure.
you know, roads change, like roads are added,
Yeah.
speed limits change, and so on.
Yep, you are, yeah. Awesome. Cool. So this last topic introduced in this notebook is the concept of a model card. Again, the model card, this is an idea of, think of it as a PowerPoint presentation for your AI model. So you want to share something about your model, but you want to share it to not only a technical audience, but also the people who will use it, people who might advertise it, people who will be somehow involved with this model. So you want to make sure that it's not at a very technical, it's also understood and read by a wider audience. So this was introduced by this 2019 paper. Take a look at it as well. And think of it as similar to a nutritional label that you find on packaged foods, right? So you don't have to be an expert in chemistry or biology or whatever is inside your food, right? But you need to know at least how many calories it has, you know, how much sugar content, sodium, vitamins, and then things like that. There's some example of model cards we're going to look at. Salesforce has one, OpenAI, GPT-3 has one, and Google Cloud as well has some interesting ones. One thing to keep in mind is who is the audience of this model card. So for example, when looking at a model card for an AI system that helps predict or interpret X-rays, then our audience will probably be medical professionals, scientists, patients, researchers, policymakers, probably. So we need to keep that in mind as well when designing the model card. What sections should a model card contain? The paper that introduced the model cards has this several sections here, 9 of them. So actually, let me start showing one. So that we can go through it together. So this is from the paper, and the goal is just looking at the model card. We should be able to understand what is it about. Okay, perfect. So let me zoom out a little bit here. There you go. So the model details, what are we looking at? And in this case, we're looking at a model developed by researchers at Google and University of Toronto. It uses convolutional neural nets and is pre-trained for face recognition and fine-tuned with cross-entropy for binary classification to detect if somebody's smiling or not. So a binary classification problem, we're looking at pictures of faces. I want to make sure that we train it well enough that it can detect when somebody's smiling or not. So that's the model detail, very high level, not super technical, just the general architecture and what is the some basic information about it. Intended use, what are use cases? What is the scope of it? Who are intended users? What use cases are out of scope? And this is another example here. So this is just for maybe fun applications. Maybe you want to have like an AI game that detects if you're smiling or not. Maybe augmentative applications where if somebody is blind and want to see if they're looking at a picture, maybe the system can tell if somebody is smiling or not, or a camera, if somebody's smiling or not. Or maybe for a search function, maybe you want to search all your photos, and maybe you want to search for photos where you are smiling or somebody, you know, in your family is smiling or your friend is smiling. What is not intended for? It is not intended for emotion detection or determining effect. Smiles were annotated based on physical appearance and not underlying emotions. Okay, good to know. Factors. So what factors affect the model? Is it maybe age, gender, ethnicity, environmental factors, the camera type, the light condition, the distance from the camera, so forth. So factors based on problems with computer vision, face technology. Some factors include, again, gender, age, race, skin type, as well as hardware factors like the camera, the photograph being taken by an older camera or a newer camera, or what lens it used, and as well as environmental factors like light, humidity, and so forth. The evaluation factors are gender and age group, and they are annotated by this publicly available dataset, Celeb A, celebrities. Other possible factors, so gender and age are determined by third-party annotators based on visual representation, and they're also broken down by male, female gender, and young and old. So just to give you an example here of some metrics, I'm going to see this soon. You see that we have, in this case, false positive rate of the entire population, just female, male, old, young, and then combination of them by age and by gender. What metrics are we looking at? So for classification system, you know, classification problems like we've seen in the past, maybe we want to look at, you know, false positive rate, false negative rate, false discovery rate, as they call it, or false omission rate, you know, true positive, true negatives, and so forth. And for regression type problems, or also known as like score-based analysis, like when your output is a score or price, maybe you want to see how your model performs across different groups. So in this case, the metrics we're looking at is false positive rate, false negative rate, as well as false discovery rate and false omission rate. So people maybe who are smiling, but our model says they're not smiling, and the opposite. So these four metrics provide values for different errors and can be calculated from the confusion matrix for binary classification systems. They also, we can use them for calculating different fairness metrics, as we saw previously in our examples. 95% confidence intervals, and then all metrics reported at 0.5 decision thresholds. And the way that they show us is using these graphs, right? So you see that for different populations, the range is much smaller. For some smaller subgroups, the range is much larger in terms of rate. So let's pick one, omission rate. We want to be as tight as possible to the center, but also we want to be as low as possible to the left. So we want to be to the left as well as close as possible to the center. Then training data. What training data did this model use? This training set here, the training data for it, and then for evaluation, the test data for it, and choosing as basic proof of concept. That was the training data. 7 was the quantitative one.
George, I have a really quick question on training data.
Mhm.
And I just wondered, it doesn't look like they addressed it, but you know, a lot of training data is not static. Models are retrained.
Mhm.
And so I think you'd have to somehow capture that in your statement to,
Got it. So
you
your
know,
training set changes, you're saying, or evolves, and your model
yeah.
evolves too.
Otherwise models can get very stale if you know, I mean, it becomes a problem of it becomes a bias if they don't retrain it, right?
Yeah.
So
Well, in my idea, once you retrain your model, I think you should regenerate this card.
yeah, would be one point. Yeah, just somehow make it so it's kind of dynamically regenerated every time.
Yeah. Because your metrics will change, your training data has definitely changed. So it's a new card at that point, I think.
Especially if you're trying to recognize individuals, right? Model trained on images of Brad Pitt from the 1980s or 90s might not work on today's version.
Got it.
That's true.
I think I missed this point, but does it say when these are necessary?
When these are necessary?
Or like when these are recommended, I mean?
You mean this breakdown or this?
No, like when you should do a model card.
Oh, so they mention it when you are trying to share it with your wider target audience. So again, this is not just technical. As you see, the description here is not super technical. It is technical enough for us to understand, but is not code level technical. So anybody who'd use this model, that would be your target audience, and that's when you would want to use this model card. So basically, it's like a presentation of your model. How would you share it with a larger audience? I don't have a good answer of when. It's a good idea to do it if you can. I mean, it's almost like a small paper of your model. There are other tools I think out there that can help you maybe automate this process of maybe generating these graphs, or maybe automating some steps. But I think most of it is very qualitative, right? You have to look at it and you have to make decisions of how it behaves. What are some intended uses? What are some unintended uses? And what are some, in the end, here there's an ethical consideration. So
I mean, more generally speaking, I think this gets at the idea of model documentation. So I guess my thought is like all models should probably be documented, or like say you're automatically training models, you should have some documentation around that. And maybe this particular format is quite suitable for cases that, especially cases that like have a big direct human impact. But I think more broadly, even if this format isn't appropriate to certain cases, model documentation still is. Otherwise, like it's truly a black box, even if it's an interpretable model.
Yeah, and you might not need all 9, right? You might just need a subset, or you might need a section that is not present here but is super important for your field. Like you can add it. This is just, I would say, like a standardized version of a model documentation. Yep, and the other one is quantitative analysis. Basically, how did your model perform on metrics you choose? You can break it down by different factors like age or gender here, or both. And the way they do that is by these graphs. The ethical considerations, sensitive data used, maybe they use insensitive data, or Does your model have any implications on health, safety, life, and how can you mitigate that, or what harm may be present in model usage? Again, these phases and annotation are based on public figures, celebrities. No new information is inferred or annotated. So basically, it's a very small subset of human faces. And caveats and recommendations: this one does not capture race or skin type, which has been reported as a source of disproportionate errors. Gender, skin type, camera details, environment, and so forth. So keep that in mind if you plan on using this model. How can you use this? Similar to what you mentioned, Alexandra, is like a way of documenting your model. So another challenge here is that maybe your organization doesn't want to reveal too much again. So maybe the description or that card is a little bit not as informative, because of proprietary data or trade secrets. In that case, they recommend these other alternatives as well as fact sheets that I think Graph shared as well. I haven't personally checked this, but maybe it's something we can look at of how do you basically, so these are designed for specific use cases and audiences, and how do you, looks like another documentation approach to me by IBM Research. Cool. And the very last exercise here, I'll look at two simple applications. One is called this Simple Zoom video editing tool, which uses AI to automatically zoom the video camera on a presenter as they walk across the room during a presentation. So basically we're having Zoom and I want to move a little bit to the left or to the right. I think I'd like the camera to stay focused on me. And if I move far away, the camera should zoom in. If I'm closer, the camera should zoom out. What audiences should you write the model card for is the first question. And so you're launching this tool and releasing a model card along with the tool in the interest of transparency. That's your interest. So model cards should be written for the groups that are most likely to read it. For a simple Zoom, such groups probably include people using the tool to record videos, organizations seeking to adopt this tool, IT and audiovisual teams and agencies, computer vision researchers, if they want to be included yet, policymakers, and developers of similar AI systems. This is a broad group, and your team can only assume a basic knowledge of video recording terms. So they don't expect your audience to be super technical in terms of recording capabilities. That is one scenario. And then another scenario, you are the product manager for another product in another company called Presenter Pro. This one is a popular video and audio recording product. Again, similar to the previous one. You want to add a new feature to your product, and you actually want to add the product from the other company. You want to basically license it from them. Yeah, very similar approach to the other product. Single camera to automatically track a presenter, focusing on them as they cross, zooming in and out, and automatically adjusting the lighting and focus of the video frame. You're hoping to incorporate the Simple Zoom, which is a different company and AI product, into your product. To determine whether Simple Zoom is a good fit, you're reviewing the Simple Zoom's model card. So let's look at it. And the Simple Zoom under intended use says that it's intended for automatic zoom, focus lighting, is not suitable for presentation in which there's more than one presenter, or in cases where the presenter is partially or fully hidden at any time. So basically, Simple Zoom developers are telling you when it works and when it doesn't work. So now if you want to incorporate this into your product, you need to be aware of that. And you have noticed that in your audience, people also use like large props, maybe something in the background or maybe something around them. How can you use this model card from Simple Zoom to basically make a decision that you want to inform your users. So the risk here is that if your audience or your customers use large props, then they could partially or fully hide the presenter. And the simple zoom model card specifically tells us that this is only meant for one presenter, where the presenter is fully shown at any time. Yep. And another one is, again, we're using this Presenter Pro, and the simple zoom model card tells us that the group factors are self-reported gender, skin tone, and self-reported age. And other factors are camera angle, presenter, camera type, lighting, how they did their evaluation data, and what metrics they used, and what quantitative analysis they used. So I think the metrics they used is they evaluated 500 presentations, and they had, I think, a human. This is a very subjective approach. So they had a human, I think, to let me zoom out a little bit, to give a score from 1 to 10 if the tracking and zooming feature of simple zoom was good enough from 1 to 10. 1 probably very bad, 10 means very good. So then something we need to look at is, how does the score change when we look at different groups, maybe by gender, by skin tone, or age. So basically, is the simple zoom doing a good job for different genders, for different skin tones, and different ages? That's something we need to keep in mind. So yeah, we need to check the model equal performance across different demographic groups, as well as maybe camera angles or distances from the camera. Another thing here that mentioned is, maybe you want to look at what is a very popular angle that your customers use, and make sure that your model performs really well for that angle. This was the exercise. There's some, in the end, they recommend taking the machine learning explainability course, which we've taken, as well as this intro to ML for people who are interested in ML, but we've taken both of them in the past.
I love how they make this intro to AI ethics course completely non-technical, accessible to non-Python programmers, non-ML backgrounds, and then next recommend, oh, now go learn about SHAP values.
Right, yeah. I think the developer is, let me remember if I remember this right.
That was
I think
Dan.
he's a lawyer, or AI ethics is in the industry and is passionate about shaping technology policy. He also, right? So he's, yeah, in law school. So maybe
No, it makes sense that the explainability one would be high on someone's list if coming out of the ethics. It's just interesting how the two courses are so differently designed.
Yeah. Cool. I just wanted to share with us some links that were shared in this course, this differential privacy that you mentioned, Robert, and federated learning, where I think, like one example, when we use the keyboard and when we swipe different words in different order. And I think Google is using this federated learning of training a model to, how do you spell something the way you swipe it, the way I swipe it, but we actually mean the same thing. This introduction to human-centered AI, I haven't checked it out yet, from MIT. People in AI guidebook. Seems like a good resource as well. Stanford also has this Human-Centered Artificial Intelligence Center, which does a lot of research. The framework that you mentioned, Robert, with the paper, and the different bias sources. This gender sage was a recent, not recent, but a project where you're looking at image classification, and you can see the impact of race, maybe, or age, or skin tone, and how different models perform. Let's see, let's go all the way to the end. So maybe by darker male or lighter male, and what is the gap, and so forth. And you can see that they don't perform as well for darker female. So they're being biased there. some controversial articles as well. Another one on fairness. The jigsaw one was interesting. The civil comments that was closed. I need to read the reason why. So notebooks on how to pre-process that toxicity data set. This is just a simple notebook of using RNNs. I think this one had a decent score. This is the image competition, I think. Yep, the inclusive image competition. The different fairness that we saw, group fairness, demographic parity, equal opportunities. This came from this paper here. All these links I put it on the Meetup page. Just a reminder of true positive, false positive rates. This impossibility theorem, I need to take a closer look. That you can basically only have design a model to optimize one type of fairness. This, I think, was what you mentioned before, Robert and Alexandra, about the attacking part of machine learning, where you change the output or the input to steer the model in a specific outcome. Equal opportunity. This one I think uses the what if tool, which is an interesting tool, and maybe we can use it for one of our projects. But I think it breaks it down by different metrics here and gives you an idea of how does your model perform across different groups. This Gini metric here, playing with AR fairness, the new conference. I want to look at maybe some more example of model cards. So yeah, the model details, the intended use, the factors, metrics, evaluation data, training data, quantitative analysis, ethical considerations, and what you should keep in mind. This paper goes in great detail, but the recommendation. And in the end, I have the one on smiling detection in images. We saw that. And the other one in toxicity in text. So you see another example here of the details. Intended use for a wide range of use cases, such as supporting human moderation or providing feedback to common authors. Not intended for fully automated moderation. Not intended to make judgment about specific individuals. Factors, metrics, ethical considerations, where the training data came from, and so forth. Salesforce has, I think, a card for different models here. GPT has a very simple one as well. Performance data limitations. I like the one from Google here on face detection. As you can see, like this is, I think, live data. So if you retrain your model, you should be able to see the limitations, lightning, trade-offs, performance. This was an interesting one. Object detection. This is very well annotated, as you can see. Yeah, and I think that's it. I'm going to stop sharing. And let me know if you have any questions or feedback. I only have one more resource to share with you before we close. Okay, then let me just share that resource that I mentioned. So next week we have a happy hour coming up. And after that, we are super excited to start a new adventure. By now we completed our Kaggle adventure. So in 2 weeks, we'll start a new adventure from Coursera called Tensorflow Data and Deployment Specialization. Some of you might have taken it, some of you might be new to you. Check it out. It uses interesting topics like TensorFlow.js and TensorFlow Lite. It's really about deploying models on either clouds or edge devices or your browser, even training them on different setups as well. It also uses TensorFlow Hub, which is a collection of models, TensorBoard for monitoring your models as they perform, and then when you serve it as well. Has about 4 courses. We'll get together to see how many weeks of course we plan to cover each time. I think a course has about 4 or 5 weeks. And I think, David, you've taken this, so this is also like heavy in terms of coding and programming, right?
It's very technical. Mhm.
Very technical, got it. Yeah.
They do for Python. It's you know, Python, you need some Python. They do guide you through the JavaScript. They guide you through the Android Studio stuff, and the I can't remember how they do the iOS one, but yeah, it's also
Awesome.
Swift or whatever and all that. So yeah, but it's very technical.
Okay, looking forward to it then. This reminds me, yeah, we did a very small sample of it in this recognize flowers step, but yeah, looking forward to taking a deeper look. Yeah, that's in 2 weeks. So yeah, register in advance, take a look, and hope you can join us for our happy hour next week. I will stop recording here. If you're joining us from YouTube, thanks again, and I'll hope to see you next week. And there's a floor open for us to discuss.